Look up at the night sky. The stars you see have been burning in place for billions of years. But imagine if, tonight, a faint, ominous red light suddenly flared into existence, right in our own solar system. For centuries, astronomers have pointed their telescopes upward, studying distant fusion reactions to understand our place in the universe. In doing so, they often compare these distant stars to a familiar object much closer to home, Jupiter. Decades of precise measurements from probes like Voyager confirm that Jupiter holds 2.5 times the mass of all the other planets combined. We also know it accreted from the same primordial cloud as the Sun, giving it a nearly identical chemical makeup of hydrogen and helium. Because of this chemical similarity, it is often labeled a failed star, but that classification is scientifically generous. The physical gap between a gas giant and an object actually capable of nuclear fusion is vast. Jupiter is a highly successful gas giant. And as we will see, the exact mass it possesses right now is a precise requirement for our continued survival. This scale illustrates the physical mass required to trigger sustained hydrogen fusion. On the left is Jupiter's current mass. On the right is the hydrogen burning limit. To become a red dwarf star, Jupiter would need an 80-fold increase in its total mass. If 79 additional Jupiters were to suddenly collide and merge with our gas giant, the resulting gravitational pressure in the core would finally overcome electron degeneracy. The temperature would spike past 3 million Kelvin, and thermonuclear fusion would ignite. Viewed from Earth, Jupiter would transform into a deep red orb. It would be incredibly dim, putting out only 3/10,000ths of the Sun's luminosity. Across the vast 400 million-mile gap separating us, Earth's surface would not register any immediate change in temperature from this new star. We would survive the initial flash. But the gravitational anchor of our solar system has just been replaced by an 80-mass wrecking ball. While Earth is initially shielded by distance, the immediate environment around the new star is subjected to intense thermal and radiative shock waves. The closest Galilean moon, Io, is already highly volcanic. The immense radiative flux from the new red dwarf would rapidly push its surface temperature beyond the melting point of silicate rock, dissolving the crust into a churning sea of glowing magma. Further out, Europa's famous ice crust would face a similar thermal assault. The entire outer shell would violently sublimate, venting enormous quantities of water vapor into space and leaving behind a massive temporary comet-like ring. Ganymede, the solar system's largest moon, possesses a thick ice mantle. That mantle would undergo runaway melting, generating a dense greenhouse atmosphere of superheated steam that crushes down on a boiling global ocean. Within a year, the local Jovian system is completely sterilized. But the true threat to the rest of the planets is moving much slower, carried entirely by the new star's gravity. In orbital mechanics, a planet's sphere of gravitational dominance is called its Hill radius. When Jupiter's mass multiplies by 80, that sphere expands violently outward. This expanded reach immediately intersects with the orbit of Saturn. For billions of years, the two largest planets have maintained a delicate, stable distance from one another. Now, that dynamic completely breaks down. The gravitational interaction drops below the critical stability threshold, and Saturn is violently ejected from the solar system entirely. By year 1000, the chaos propagates inward. The immense gravity begins to pull at the millions of rocks sitting between Mars and the new star. This orbital map of the inner solar system models the result. Jupiter is frequently described as a shield that protects Earth from debris. But at stellar mass, it acts as a chaotic gravitational sweeper, completely destabilizing the asteroid belt. Millions of rocks are nudged into new trajectories that cross the inner planets. Earth would face a relentless, sterilizing barrage of impacts. With Saturn gone and the asteroid belt scattered into our path, the inner solar system is left entirely defenseless against the shifting gravitational tides. Over 10,000 years later, a slow, invisible force takes hold. Astronomers call these long-term orbital interactions secular resonances. Jupiter's continuous pull stretches Earth's orbit into a highly eccentric ellipse. Dragged near Venus and thrown toward Mars, Earth bakes near the Sun and deep freezes retreating outward. Eventually, extreme perturbations overwhelm local gravity, stripping the Moon entirely away. Without the tidal torque of the Moon to act as an anchor, Earth's axis descends into chaotic obliquity. The poles shift erratically, dismantling whatever climate systems and ecosystems manage to survive the asteroid bombardment. Earth is reduced to a dead, barren rock, violently swinging through space. The stability that allowed human civilization to flourish is gone. Yet, if we look back to the epicenter of this disaster, there is a cosmic irony waiting at Callisto, the outermost of the Galilean moons. Callisto sits at just the right distance from the new red dwarf to fall precisely within its habitable zone. The radiative flux is nearly identical to what Earth once received from the Sun. Callisto's ancient surface ice would melt, stabilizing into a global liquid ocean with temperate, Earth-like conditions. The solar system operates like a delicately balanced clock. Every planet relies on the current mass of the others. Jupiter's failure to gather the material needed for stellar ignition is the exact reason we are here to observe it. If humanity saw this chronological sequence of destruction coming, it poses a difficult question. Could we abandon a dying Earth and migrate to Callisto in time? Or would the gravitational chaos of our newly reshaped solar system swallow us first, long before we ever reached our new ocean world?